Hello ladies and gentlemen. In the last video we have seen an SR latch. That's a combinational circuit in which we use positive feedback to store a bit or latch to some value, a logic 1 or a logic 0. Now it is not a flip-flop, but we can make it into a synchronous circuit by applying, extending that circuit to include a common clock. So as I told you, in sequential circuit, there is always a common pulse signal that's very unique to, that feature is very unique to any sequential circuit. So in this video, we will see a clocked SR flip-flop with both NAND and NOR in both NAND and NOR configuration. And we will discuss its truth table and simulations. So let me start with that presentation. So the speech is organized into your learning outcomes, then SR flip-flop with the NAND gate and its simulation with the QUCS. Then NAND based SR flip-flop with Verilog. We will see a Verilog module for the SR flip-flop. Then a NOR based SR flip-flop, its truth table and the simulation in QUCS. Then NOR based SR flip-flop with Verilog, and then the summary of understanding. So what you will learn in this video is that you will learn the operation of SR flip-flop with a NAND with the clock and simulate it in QUCS and Verilog. Then that way you can verify its truth table. Then you will learn the operation of SR flip-flop with the NOR. With the NOR circuitry, how do you make an SR flip-flop? And then you simulate it in QUCS and Verilog. That way you verify the truth table. Then you will understand the forbidden state in an SR flip-flop. Now this is a circuit diagram of an SR flip-flop with the NAND configuration. Now earlier here in place of here we had two inverters. Instead now we put two NAND gates. One input is given at the first NAND, let that be Sn. N denotes the nth clock cycle. And here I give Rn, and the other two inputs, they are shorted together and a common clock is applied. So this common clock can be a pulse signal. Here in the case of NAND circuitry, this clock is a positive going pulse, is an active high pulse. So only if this clock is active, this S and R will have some effect on the output Q and Q bar. Now this index n is something very interesting. This is Sn is the and Rn are the inputs at the end the clock cycle, and this these are the outputs in the next clock cycle. These are the Qn plus 1, that is the n plus first instant, and this is Qn plus 1 bar. No, this circuit is a synchronous circuit. Even if this Sn and Rn change, Qn plus 1 and Qn plus 1 bar need not change. What happens is it waits for this clock cycle. Only when this clock goes positive, then only this Qn plus then only the change in Sn and Rn will be reflected at the output. Okay, so this is a previous input Sn and Rn, and this is the next state Qn plus 1 and Q bar n plus 1. Now let us look at its operation. Now I told you that this clock is an active high clock. So if this clock is 0, what will happen? This output A and B will be high. So if this is A and B are high, then output of this will be A1 and Qn plus 1 bar all complement, that is Qn plus 1, and this is Qn plus 1 and 1 all complement, that is Qn plus 1 all complement. Now what is this? What is the meaning of that? That it stays in the previous state. So if the clock is inactive, the flip-flop continues in its previous state without any change. Now what will be the value of Sn and Rn? Now that is the meaning of a synchronous circuit. Now what if this clock is positive and I apply these inputs? Now we have to see that we have to understand the truth table. Now what happens, this Sn and Rn are zeros if this clock is high, and if you look in the first column of this first row of this truth table, you can see that if the clock is high and if Sn equal to Rn equal to 0, so this output A and B are high, so that remembers the previous state. As I said earlier, this is 1, this is Qn plus 1, this comes here, this whatever value here, this comes here and appears at Qn plus 1. This is Q bar coming here, Q bar and 1 all complement, that is Q bar Q bar, so qn plus 1 remains qn plus 1, so that remains in the previous state. So here this is qn plus 1 and 1 whole complement, that is qn plus 1 whole complement. So this remains in the previous state. So whatever state it was in, say if it was earlier in 1 0 position, it will continue in 1 0. If it were in 0 1, it would continue in 0 1 position if the inputs are 0 1 0. Now, what if this input, that is, it remembers the previous state. What if this input S is 0 and R equal to 1 and the clock is high? If this S equal to 0, that means A will be 1. Okay, A will be 1, because if one of the input one NAND is a low, output becomes a high. And this will be, this Rn is a 1. So here it is a 1 and 1 complement. This becomes a 0. Okay. So this is a 1 and this is a 0. So whenever the one of the inputs is a 0, if this is a 0, then this qn plus 1 bar output, this goes to 1. Okay. So as this goes to 1, this is a 1 here, 1 and 1 whole complement, qn plus 1 become a 0. So it goes to the states 0 1. So that is what is happening here, 0 1. That is a reset condition. S equal to 0 and R equal to 1. This is a reset condition. Qn plus 1 is 0 and Qn plus 1 complement is 1. Now I will say that again. S equal to 0, R equal to 1. When S equal to 0, A becomes a 1. And where if R is equal to 1 1, this clock is high, so 1 and 1 whole complement, it becomes a 0 here. So A is a 1 and B is a 0. Since B is a 0, this output becomes a 1. Okay. So when this output is 1, this is coupled here, and 1 and 1 whole complement, it becomes a 0 at qn plus 1. So qn plus 1 is 0 and qn plus 1 complement is a 1. So that is a second case. That is a reset condition of NSR flip-flop. Now what if with an active clock, if Sn equal to 1 and Rn equal to 0, that is the third line of the truth table. Now if Sn equal to 1 and Rn equal to 0, if Rn equal to 0, B becomes a 1, and here A becomes a 0. Because this is Sn is 1 and clock is high, so 1 and 1 whole complement. So this becomes a 0. If this is a 0, qn plus 1 becomes a 1. When qn plus 1 is a 1, it is 1 and 1 whole complement. Qn plus 1 bar becomes a 0. So that is qn plus 1 is 1, qn plus 1 bar is 1. So it's a set condition. It's a set condition in an SR flip-flop. Now I'll say that again. Sn is 1 and Rn equal to 0. If Rn equal to 0, B becomes a 1. Sn is 1, clock is 1, so A becomes a 0. When A is a 0, qn plus 1 becomes a high. When qn plus 1 becomes high, it is coupled here, fed by here, so 1 and 1 whole complement, qn plus 1 bar becomes a 0. That is a set state in a NSR flip-flop with an NAND. Now let us look at the last case, that is with an active high clock. If Sn equal to Rn equal to 1, if Sn equal to Rn equal to 1 and clock is high, this both A and B goes 0. When A and B goes to 0, the output of both these NAND gates, they tend to be high, which is illegal. So what happens is in practice, this drives to an indeterminate state. It can be either in a 1-0 condition or in a 0-1 condition. So this is a forbidden case. That is, with S equal to 1, R equal to 1 and an active high clock, both A and B becomes a 0. When A and B become a 0, both the Q and Q bar output is driven to high, which is impossible. This is forbidden. So that S equal to 1, R equal to 1 is a forbidden condition. So this is how the truth table of an SR flip-flop look like. Now let us see this simulation in QUCS. Now here I have my SR flip-flop with NAND. This circuit we have seen. I have driven it with some signals. This 20 nanosecond, 20 nanosecond, that way. Now what happens is I run a simulation. Now you can see here, yeah, the waveform is there, but let me focus on this truth table. When S equal to 1, R equal to 1, that is they are in an indeterminate condition. They are in indeterminate condition. Now when S equal to 1, R equal to, but this is not, the problem is it is not in an indeterminate state. The clock is low. So the clock is low means this circuit is not active at all. So initially it is in some indeterminate condition, that's all. Now here it is S equal to 1, R equal to 0, and clock is 1. Clock is active, and Q is 1 and Q bar equal to 0, as we said earlier. That is a set condition in an SR flip-flop. Now then this S and R are driven to 0 0, but clock is 0. Okay, clock is 0 means the circuit is not activated. The inputs have no effect on the output, so it remains in the previous state 1 0 1 0. Okay. Now the second case is 0 1 with clock 1. Clock 1 means clock is active, so this the output of Q will be 0 and Q bar equal to 1. Now this is again 1 0 with clock 0. Clock 0 means circuit is inactive, so it remains in the previous state 0 1 without any change. And then there is 1 0 with the active high clock, the output goes to 1 0. Then it is 0 0 0 1 0 1 with a 0 clock, again it remains in the previous state. 0 0 with the clock 1 means now this clock is high. The clock is high, that means circuit responds to this S and R inputs. Now what is S equal to 0, R equal to 0? That is when it remembers the previous state. Now it remembers the previous state. This is not earlier. Here in this case, if you say here, this is not due to any remembrance of the previous state, but because the clock is inactive. But here the clock is active, and it remembers the previous state 1 0. It remains in 1 0. So this is how I verify the truth table of SR flip-flop. At home you can develop such circuits and verify the operations. Now let me go back to my presentation. Now let us make a gate level Verilog model for the SR flip-flop. So what I do is I start with a keyword module and end module, and I give some names, SR flip-flop, SRFF, and I have two outputs, Q and Q bar, and three inputs, S, R, and clock. Now those Q and Q bar are set as output wires, and S, R, C, K are put as input wires. And now in between I have this A and B. This is the output of your first AND gate. So I need some local nets for that. So I declare them as wires. Wire S bar, R bar. Now the first NAND gate output, what goes into the NAND gate are S and clock, and S bar comes out. What goes into the second NAND, it is R and clock, and R bar comes out. Then these are the two NAND gates at the output section, NAND N3, Q, S bar and Q bar. Then N4, that is R bar and Q goes in, and Q bar comes out. Now let us see, let us simulate this with iVerilog. Now this is the module we made, and I have written a test bench for this. What I have to do is the device under test is srff.v, so that I have to include here grave include srff.v. Then I start with a module test bench. Some name, I give the name test bench, and SR clock, they are the inputs, they are given as registers, and Q and Q bar are outputs, they are given as wires. Then I have to make an instance of my SR flip-flop. I give srff, I say some name y1, and Q bar SR CLK, just the same way I give here Q bar SR and CLK. Now then I initialize some values. I say that this Q bar, they are all binary, and then I define a file, declare a file for that, say srff.vcd for storing the waveforms. And then I give some patterns like S equal to 0, R equal to 0, clock equal to 1, that way. Okay, then we can run this code and appreciate. I have to open a terminal here. I will make it a little bigger. Okay, now I type here iVerilog. Now this is the device is compiled without any error. Now I go to srff tb -o a.out. Now you can run a.out Now you can see this happening. Initially at say 0 nanosecond, everything is in an indeterminate state. At 10 nanosecond, S equal to 0, R equal to 0. So it remembers the clock is active high. So it remembers the previous state. Previous state is indeterminate. So it remains in the indeterminate state. Now at the 15 nanosecond, S equal to 0, R equal to 1 and active high clock. So this is a reset condition. So Q becomes a 0 and Q bar becomes a 1. And at 20 nanosecond with the active high clock, S equal to 0, R equal to 0. So here it is a previous state, so it should remain at 0, 1. It is happening. Q equal to 0 and Q bar equal to 1. You can see that the flip-flop retains the previous state. And here at 25 nanosecond with the clock equal to 1, S equal to 1, R equal to 0, this is a set state. Here Q should become 1. Here Q becomes a 1 and Q bar becomes a 0 as predicted, as we argued in the truth table. Again at next say 30 nanosecond, S is equal to 0, R equal to 0. So again it remembers the previous state. It is 1 0. Previous state was 1 0. It remains in 1 0. Then at with the clock equal to 0, you don't see anything. Now we haven't seen the last condition. Okay, maybe we will incorporate it here. I will make this a 1. I will recompile this. Now we can see that here with the clock equal to high and S equal to R equal to 1, you see that both the Q and Q bar goes to high, which is illegal. But in this is being a simulator, it can happen. But in actual practice, when you do with actual circuits, it goes into some arbitrary state with Q and Q bar as complements. Now let me go back to my presentation. Now let us rewire this circuit with the NOR. So with an OR NOR SR flip-flop will look like this. Only thing is I have replaced those NANDs with NOR. Now the property of the NOR is that if one of the input to a NOR is a high, the output is a low. And if all inputs to the NOR is a low, then output becomes a high. Now here the difference from the NAND circuit is that the clock should be active low. Because with an active high clock, what will happen is both A and B become 0. Because if this is high, if the clock is high, irrespective of Sn and Rn, the outputs of this NOR will be low because A will be 0 and B equal to 0. So what will happen is if this B is 0, then here this what comes is a Q complement comes here. 0 or Q complement or all complement, it becomes a Q here. And Q comes here, and Q or 0 all complement becomes a Q complement here. So that means it remains in the previous state. So if the clock is active high here, that means the circuit is not enabled. The inputs have no effect on that. The outputs remain lasted in the previous states. Now let us see what will happen. The clock is high, and if the clock is high and if S equal to 0, R equal to 0, what will happen? Now if the clock is low and if S equal to 0 and R equal to 0, then both of these output A and B will become high. Because this is 0 or 0 complement, this is 0 or 0 complement, both A and B becomes a high. So when both A and B become high, what will happen is both Q and Q bar tends to be low. Because if one of the inputs is a high, the output becomes a low. So when A and B are high, then Q and Q bar becomes a low. So when Q and Q bar, this is a forbidden condition. So here in the case of SR flip-flop with NOR, 0, 0, S equal to 0, R equal to 0 gives you the forbidden condition. Now, so you have understood the first line of the truth table. Now let us look at the second line of the truth table with S equal to 0, R equal to 1 and clock equal to 0. So S equal to 0, R equal to 1. When S equal to 0, R equal to 1. When R equal to 1, B becomes a 0. Okay. When S equal to 0 and clock equal to 0, A becomes a 1. When A is a 1, Q output becomes a low, because when one of the inputs is a high, output becomes a low. When this low and this low here, 0 or 0, all complement becomes a 1 here. So Q becomes a 0 and Qn plus Q bar becomes a 0. Q becomes a 0 and Q bar becomes a 0, 1. I will say that again. With S equal to 0 and R equal to 1 and clock equal to low, when R equal to 1, B becomes a low. When S and clock are low, A becomes a 1. When A becomes a 1, Q output becomes a low. When Q output becomes a low, here two lows come here, that is 0, 0 whole complement, and Q bar becomes a high. So Qn plus 1 becomes a 0 and Qn plus 1 complement is a 1. So this is the reset condition in a SR flip-flop with a NOR. Now let us look at the third line of this truth table, 1, 0, and clock is low. When S equal to 1, R equal to 0. When S equal to 1, A becomes a 0. When R and clock are low, this becomes B becomes a high. When B becomes a high, Qn plus 1 complement, this becomes a low. And this low and this low here, 0 or 0 all complement becomes a 1 here. So Qn plus 1 becomes a high. Qn plus 1 becomes a high, and Qn plus 1 bar is a 0. Now I say that again. When S equal to 1, R equal to 0, and clock is low, what will happen? When S equal to 1, A becomes a low. When clock and R are low, that is 0 or 0 whole complement, B becomes a high. A equal to 0, B equal to 1. When B equal to 1, Qn plus 1 bar becomes a 0. This output becomes a 0. When this output and this together, 2 0, 0 or 0 whole complement, Qn plus 1 becomes a high. So with S equal to 1, R equal to 0, Qn plus 1 is high and Qn plus 1 complement is a 0. Now let us look at the last case with S equal to 1, R equal to 1, clock equal to low. When S and R are 1s, A and B are both 0. So what will happen is here this Q bar will come here. Q bar or 0 all complement is Q, and Q comes here. Q or 0 all complement is a Q bar. So it remains in the previous state. It remembers the previous state. That is with this, that system has a memory. It remembers the previous state. So with the S equal to 1, R equal to 1, it remembers the previous state. With S equal to 0, R equal to 0, it is in indeterminate state. This is how the SR flip-flop using NOR works. Now let us look at the simulation of this in QUCS. Now I have my NOR circuit here, and here I have applied some signals, and I can run some simulation. You can see the simulations here. So here you have S equal to 1, R equal to 0, so clock equal to 0, so circuit is active, so it is in 1 0, that is a set condition. Okay, that is S equal to 1, R equal to 0, that is Qn plus 1 is 1 and Qn bar is 0. Now with 1 1, you can see that the clock is high, so it remains in the previous state, because clock is inactive, it remains in the previous state. Again the clock is low, and here it is 0 and 1, so the output becomes Q becomes a 0 and Q bar becomes a 1. Now it is a 0 0 with a clock 1, again the circuit has become inactive. Then I have 1 1 with a 0. 1 1 with 0 means it remembers the previous state. Now the circuit is active because the clock is low, and it latches to the previous state, that is the previous state is 0 1. Again clock has gone inactive. Okay, so this is how I verify the truth table of SR flip-flop with a NOR using QUCS. Now let me go back to my presentation. Now what I have to do is I have to develop the circuit in Verilog. All I have to do is I go to the other circuit for SR flip-flop with a NOR and with a NAND, and replace all NAND with a NOR. That's the only change I have to make. NAND with a NOR. So this is the only change I have made. You can search and replace a NOR with a NAND with a NOR, and there you have. Now we will see the simulation of this. Here if I come here, here is SRF of NOR and SRF of NOR TB. Now I'll close the previous two. Now this is my SRF of NOR. I give some name SRF of NOR, and output Q bar, and input SRCLK. Then internal nets S bar and R bar. This then 4 NOR gates, just like the previous case, except that the NAND is replaced with NOR. Now I write a test bench for this. All I have to do is I have to make some slight changes. I make a grave include SRF of NOR, then other things are almost the same. Then I give some inputs signals with a clock. Okay, then I have to run this and appreciate. Now I will run Verilog. .v. Now that device is compiled without any error. Now I have to run the test bench with some output minus OA dot out. Now at 0 nanosecond everything is in an indeterminate state. At 10 nanosecond you have S equal to 0, R equal to 0 with active low clock. So what happens is Q and Q bar both tend to be 0. This is a forbidden state. This being a simulator, you can see that both Q and Q bar becomes a 0, but in actual practice it will get to some value. Now in the next clock cycle, that is at 15 nanosecond with the clock equal to 0, S equal to 0, R equal to 1. Now Q becomes a 0 and Q bar becomes a 1. This is a reset condition. And at 20 nanosecond again the clock is low, so the circuit is active. S equal to 0, R equal to 0. Again it is driven to an indeterminate state, a forbidden state. At 25 nanoseconds clock is active and S equal to 1, R equal to 1. Now Q becomes a 1 and Q bar becomes a 0. That is a set state of the SR flip-flop. Now at 30 nanosecond again this is S equal to 0, R equal to 0. Again it's an indeterminate condition, a forbidden condition. And at 35 nanosecond S equal to 1, R equal to 1. Now with the clock equal to 1, so this with the clock equal to 1, what will happen is this circuit is now inactive. Okay, it goes to some state, it remains in some state. And S equal to 1, R equal to 1 with clock equal to 0. Now whatever state was there, it was earlier Q1 and 0, so it goes to Q equal to 1 and Q bar equal to 0. It remembers the previous state. Again with the clock equal to 1, S equal to 1, R equal to 1, this Q remains the same, because this is not a set condition due to inputs, but because the circuit is inactive, because the clock is a 1, so it remains in the previous state, because the input signals S and R do not have any effect on the output. Why? Because the clock is inactive. So let me go back to my presentation. Now, coming to the summary of what you learned, in this video you learned the operation of SR flip-flop with NAND and simulated with the QUCS and Verilog. So you understood the truth table, you verified the truth table with the QUCS and Verilog. Then you learned the operation of SR flip-flop with the NOR with the clock and simulated it with the QUCS and Verilog. You can see that the conditions are reversed, like the memory and the indeterminate states, the conditions are reversed between NOR and NAND. Why? Because they respond differently to signals, NOR and NAND. Then you understood the forbidden state in SR flip-flop. This is very important. Now in the next classes we will be making modifications in this SR flip-flop so that that forbidden condition is removed. So we will end up with something called a JK flip-flop. So that is in the next class. So that is the end of this presentation. I thank you all.